Okay, so today we'll be focusing on Laplace transform. So Laplace transform, whatever we'll able to finish today will be on the exam, and then tomorrow we'll be work on your questions. Like if you have any question in assignment or review, then we can work it out that one. Okay, so what is the motivation behind Laplace transform? Well, Laplace transform helps us to convert a differential equation into an algebraic equation. So what do I mean by that? So algebraic equations are also not always easy to solve. So for example, if you have this as an algebraic equation, x equals to 10x, and I ask you find all the values of x such that x is equals to tan x. So this is an algebraic equation, no derivative, nothing. So what are the values of x? You can give one very quick value of x such that x is equals to tan x. 0, right. So 0 is satisfying this. Now how will you determine other points? Are there points where x is equals to tan x?
Cosine and sine are equal. So is that
Cosine sine equal would give it 1.
Yeah.
That would give 1.
That'd give 1.
So if this problem is given in a calculus class to you, not in the differential equation, say calculus 2, you can do it in calculus 1 also, but say calculus 2. So when do we say two functions are equal? Geometrically. When the graph of them will be intersecting each other, right? So fx y equals to x is a straight line, and the function tan x, if you draw the line y equals to x, the points where it will intersect the tan x function, that many point of intersections are there of both the graphs. Now if I specify an interval, then you will have finitely many solutions to this equation. But if I don't specify the interval and ask this question, I'll ask this question on a real line, then there are infinitely many points, because the tan graph will go asymptotic and the line will keep cutting those graphs. So so we can yes, right. So because tan graph repeats, right? I mean, if you have y equals to x, that is a straight line passing like this. Now how will the tan x graph will look like? So from negative pi by 2 to pi by 2, and it will pass through origin, the curve. So will it be negative this side or will it be positive this side? It will be positive this side, right? That's the straightforward. Okay, so this, it will be asymptotic like this, and there is a bulge here, and then it will be moving up like this, right? So at this point it will intersect, but since it is going, it's repeating its behavior again from here and will intersect at a point pi, and then so all the places this line is, we can extend it, and now this graph are also continuing in this direction, positive y-axis, so they keep cutting. So there are so many solutions. Okay, now Laplace transform, what it is doing, it is converting a differential equation into algebraic equation, and then we are left with solving equations which involves x, or like, yeah, so that's what we will be solving. But what is another significance of Laplace transform? So far we have learned how to solve differential equations like this, right? You know how to solve this differential equation. But if I give you a differential equation y double prime minus 2y prime plus y equals to fx, where fx is 1 when so I was knowing that. Okay, so fx is, let me do this so that we won't lose if I erase. Okay, so fx is 1 when x is between interval 0 to say 1/2, and fx is taking a value -1 when x is bigger than 1/2 and less than 1. So now fx function is changing in this interval, changing its value. Do we know any method how we will solve this differential equation? Can we solve this from method of undetermined coefficient or variation of parameter? No. Method of undetermined coefficient, this function is not continuous. So we haven't learned any way how to handle this. Variation of parameter, no, with that also. So this we cannot solve with the methods we have for second order differential equation. How we will handle the right hand side which is discontinuous? Laplace transform helps us to do that. So using Laplace transform we can solve this differential equation, where fx is piecewise continuous will work as well. Piecewise continuous function means discontinuity at finitely many points. Now if the discontinuities are at infinitely many points, then also we can do the Laplace transform, but the function has to be of spatial type. Say the discontinuity is at n pi, so it's kind of like periodic function, so then we can handle even though there are infinitely many discontinuities. But if there is no pattern there, then it's little difficult and out of the scope of this particular course. So we will be handling piecewise continuous, finitely many discontinuity, as well as we will be dealing infinitely many discontinuity, but the function is periodic. This function repeats exactly same after the point of discontinuity. Okay, so Laplace transform is a function of s, and what we are doing is we are multiplying e to the power minus sx. So let me zoom in this portion here. This is nothing but, or rewrite it with the pen, e to the power minus sx fx dx. So we are integrating this expression with respect to which variable? With respect to x. So we will be plugging the limits in x. So this is eventually a function of which variable? Once you integrate it and plug in the limits, then s is left, right? So it's a function of s, and that's the reason I put here capital F of s. Now this is a Laplace transform of this function fx. Okay, what actually is happening here is this is kind of a weight which we are multiplying in a function, and we are getting a continuous function. Any discontinuous function, if you integrate it, it will give rise to a continuous function. So this capital Fs here will be continuous. Integration increases the regularity. Differentiation decreases the regularity. Okay, so we get here now, this is since a function of s, so it will be algebraic expression involving s square and those kind of terms, or maybe e to the power 2s or 3s. Okay, so what is the domain of this capital function f? These are the very important question we should ask. Well, if this integral, it's an, as you can say, it's an improper integral because it's going till infinity. If this integral converges, all those value of s for which this integral converges will be in the domain of this function. So f is a domain of f is set of all real numbers s for which this improper integral converges. So given any function, Laplace transform of that function is nothing but 0 to infinity e to the power minus sx fx dx. Okay, so this is Laplace transform. Now, since this is a function, we are doing like integral. If it's a sequence, we will be doing summation. How many of you have done this Riemann, Stieltjes integral, upper sums, lower sums, and then you try to say upper sums equals to lower sum, then it is integrable? You did in Cal 3, right? This thing. So when it is a series, then you would consider partial sums and see whether it converges. You take a partial sum, find the partial sum, then take limit n approaches to infinity, and that's how you get for the discrete case. Okay, at any rate, let's move on. So let's find out the Laplace transform of some simple functions. Say I want to find out Laplace transform e to the power x. So by definition it will be 0 to infinity e to the power minus sx, fx here is e to the x dx. So this is by definition of Laplace transform. So I will combine the terms here, e to the power minus s plus 1 x 0 to infinity dx. E to the a times e to the b is e to the a plus b. So we have this expression. What is the integration of this? Minus s plus 1 divided by minus s plus 1, and then I have to take limits. So since it is 0 to infinity, it will be better if I write limit x approaches to infinity minus and plug a 0 here, so it would be e to the power minus s plus 1 times 0. Right? So this is just 1. Okay, what happened to the term, this term? What is limit x approaches to infinity of e to the power minus s plus 1 x divided by 1 minus s, and this is here minus 1. Because you have upper limit minus lower limit in the integral. Do we have to divide this by minus s plus 1?
That's what I was going to ask.
Yeah, we have to. So this is minus 1 over minus s plus 1. Okay, so upper limit minus lower limit we did. This is just 1. It's fine. What happens to this term as x approaches to infinity? What can you say? Tell me, what will happen to this term? This 0 is not here, this is in the integral. This will go to When will this go to infinity?
Oh,
When S is equal to 1.
when S is I'm trying to figure out how to say it. When that negative S term.
So okay, let me make it easier for you. I am pulling the negative sign out, and I am doing this now.
When S is greater, when S is less than 1.
When S is less than 1, this is going to.
Oh, when S is greater than 1. No, less than 1. Yeah, because you want that negative, and then the negative cancels it, so you get a positive infinity. You're trying to avoid going to negative infinity.
Which one will be helpful to me?
Approach to 0.
It approaches to 0 when?
It's 1 over.
When it approaches to 0 when S is greater than 1. And that's what I want. I don't want it to go to infinity, right? I want it to go to 0. Because then it will converge. If it goes to infinity, it's not converging. So, S bigger than 1, this whole thing will go to 0. Because e to the power minus of positive number times x will go to 0. And you are left with equals to 1 over. So, you have a negative sign here and negative here. So, you can say this is s minus 1. Right? Multiply with the negative sign in this. So, you get s minus 1. So, Laplace transform of e to the power x is 1 over s minus 1 where s is bigger than 1. So, what is the domain of this Laplace transform? Domain of this function here is all s values which are bigger than 1. So, it's very important whenever you write down a Laplace transform, you specify the domain of a function where it is defined. If it's not defined at s equals to 0. Right? So, you have to be specifying this. Okay, similarly, if I want to find out Laplace transform of e to the 2x, only change here is 2 comes up here, and let me not do in this. How about I copy it and put all this below here and then make changes. Okay, let's try. Why it's not? Okay, so here 2 will come, right? Here 2 will come because now you have 2x. This term will become 2. This term will become 2. Denominators will become 2, right? Because of this 2 here. And then you have here 2. And all these ones except this one is getting changed to 2. Right? Because 2x, it will become minus s plus 2. Okay, then integration 2 will come in the bottom. Then limits once we will take, 2 is up here in the bottom and then 1 over this, because this 1 is because e to the 0. So we get this. Okay, so then Laplace transform changes to what is the domain of for this function? It has to be greater than 2. So this should be 2 here instead of 1. And then this is 1 over s minus 2. So in general, then you can say Laplace transform of e to the ax is nothing but 1 over s minus a, where s is bigger than a. This is like a general formula. For Laplace transform of e to the ax. Right? So you can do this way. Now if a is negative, will it make any difference here? No. I will just replace this by 1 over s plus 1. and now my s will be bigger than not 2, not 1, minus 1. So you can check after doing, like, if you do the calculation, same thing, you are just replacing a by negative 1 here, and that's it. Okay, so this is exponentials. So everybody is okay with e to the x Laplace transform? Let's go to trigonometric function. Okay, before that, let me give you one thing. There is a reason why I wrote down in the definition this curly L here, and not, and let me be careful here, not the L which we had written down before in the notes, like L of f of x. Laplace transform, we will be using this symbol. Well, since it's an integration, it is nothing but Laplace transform is also linear, and we will see that, and that property is extremely helpful when we will be solving differential equations. Okay, so let's show why this is a linear operator. The reason this is helpful is, most of the time you end up finding a Laplace transform of, say, x plus e to the x, say. If you have to find the Laplace transform of this, you don't have to put this back in the definition and integrate it. What you can do is, you can find them separately and add it. So this is where linearity comes into play. That if it's linear, you can, from the table which will be given to you in exam, you can see the Laplace transform of x, e to the x, and you find them and you add them. That's it. You don't have to plug this function back up there. So here, this is a table which I will provide you in exam on Friday, and it has some functions and their Laplace transform up here. This will be on the blackboard also for your reference. And now here you can see, for x, if you want to find Laplace transform e to the ax, which is 1 over s minus a, and for x, maybe this one is working, so you can take n to be 1. So if n is 1, it is 1 over s to the power 1 plus 1, which is 2, so 1 over s square, right? So 1 over s square will be the Laplace transform of x or t, whichever the function is f of t, then it's in here. But Laplace transform remain in s. Only thing is, independent variable in function can be x or t. That's a big simple.
And the ranges, are they like the union of the two, or are they the same? The ranges would be different.
Range would be intersection, not union. Intersection. Not range, I should say domain.
Oh, yeah,
So the values of s for which this Laplace transform is defined, and the value of s for which this Laplace transform is defined, you would take, well, it's addition here. You will take what values of s for which the Laplace transform of both of them is defined, right? So then you basically consider intersection here of the domains of s values. Okay, so L is a linear operator. Let's check. So let ux and vx be two functions, piecewise continuous, I can say, piecewise continuous functions. Then Laplace transform of ux plus c times vx, where c is a real number, scalar, is nothing but, by definition, e to the power minus sx ux plus c times vx dx. Now since it's a multiplication here and integration, I will first multiply and then we'll distribute this integral on both the terms. So first I am just multiplying with e to the minus sx on both the terms, both the functions, and then I will distribute this further integral as well. So integral of the sum is sum of integrals, and c is just a scalar, you can pull it out. So if you pull out the c, you will get what? What is inside these integrals? Product of function, that's right, but what are these integrals? This whole thing is Laplace transform of ux and c times Laplace transform of vx. So since this splitting happens naturally because of the integral, because of integration, therefore Laplace transform is also linear, and that helps us to not to put these complicated function all together in the definition, but we can separately find the Laplace transform and add it up later on. Okay, so this is there. Now let's try to understand another properties of Laplace transform. What if I want to find a Laplace transform of a derivative of function? Because eventually, what is my goal? What is my final goal of learning Laplace transform? Solving the differential equation with discontinuous right hand side, right? That's a final goal. So big picture is we need to solve differential equation where right hand side is discontinuous, and that's the reason we are learning Laplace transform right now. Okay, so if we have to do that, then well, there is a second order differential equation, say y double prime minus 2y prime plus y equals to fx, and as we have taken this example before also, 1 between 0 and half and negative 1 between half and 1. What I will be doing is I will be taking a Laplace transform both the side. Of this equation. Now, can I find the Laplace transform of this function, which is this, which is written here? I mean, I can find. Can we find the Laplace transform of this function? Now, table is not giving you this. How will you find the Laplace transform of this function? This function is discontinuous at x is equals to half. This function is only defined between 0 and 1. So if I write down my definition for a moment, it is nothing but 0 to infinity e to the minus sx fx dx, right? That's Laplace transform. But this function is not even defined after 1 and below 0. So this whole thing, this integral boils down to integral from 0 to 1. Okay, so e to the minus sx fx dx, because f is not even defined, so we would be focusing only in this interval. Now in this interval, how will I integrate this function f, which is discontinuous at a point half? We can do that, right? We can split the integrals minus sx dx. At a point of discontinuity, we can break the integral. And function value is negative 1 here, so let's multiply by negative 1. Function value is 1 here, so multiply by 1. Now integration of this is easy. and plugging these limits, this will always converge for all values of s. Now the question here is, I will place here whatever I'll get from this calculation. Say, how will I handle the left hand side? Now one thing you know about Laplace transform, they are linear. So you might say, well, let's split all these terms. Now y is a function which is unknown, and we are looking for the solution of this differential equation. We are looking for y. Laplace transform of y is coming up here. Y we don't even know. What is y? L of y prime, because we are solving for y. So we don't know what is y. We need to find an expression of Laplace transform of y prime in terms of Laplace transform of y, and we need to find expression of Laplace transform of y double prime in terms of Laplace transform of y, so that we can get every single thing here in Laplace transform of y. We can take it common and try to find just a Laplace transform of y x in terms of s. Still we don't have function. Then the next strategy, which I will be going over next week, will be inverting a Laplace transform. Inverse of this and getting back my function y. And that's how we will eventually solve these problems. So the big picture is, we will split the left hand side, we will try to convert this into Ly, Laplace transform of y, everything, and we will compute the Laplace transform of right hand side. Then once we have Laplace transform of yx in terms of s, we will invert it to get the function y. Okay, so our goal right now is, first tiny intermediate goal is to find the Laplace transform of y prime in terms of y, Laplace transform of y, right? So this is an expression for that. It's a formula. I will explain how these you can see clearly why they are true, and then we will start applying it. It's just then we will be applying it again and again in every problem. Okay, so let's see here. Laplace transform of y prime x by definition should be equals to 0 to infinity e to the power minus sx y prime x dx, by definition. So now we can do integration by parts here. So which will be my first function? What's the first function? u dv, v du, whatever you do.
So the y prime, it might be the second one
Because you integrated to get back. Yeah, exactly. So you would take maybe this as a first, and this one is a second function. Okay. So first function, integral of second, differential of first, this is what you will get. Now this one, this is not really appropriate way of writing 0 to infinity. This is not, this you should not write this, even though I have written like this. You should write like this: e to the power minus sx yx minus, place a 0 now, minus minus plus 0 to infinity e to the power minus sx over s yx dx. So what I did here, upper limit infinity, I am taking like limit x approaches to infinity into this, and by lower limit y is a function of x, it's a computation of y at 0, e to the 0 is just 1. Then this negative sign get cancelled with this negative sign, and we get e to the power minus sx over s times yx. Now if I pull this s out of this integral, by the way, is it right? I see a problem here. What's the problem? There is a problem here. There's a problem in this step right here.
Yes, it's negative.
S has to be greater than 0.
No. There is a problem in integration by parts. No, it should not be x square. Will it come in division or will it come in multiplication? It should be negative s times e to the negative sx. Okay, right, you have to differentiate it. So this s is coming in the numerator, not in the denominator. Okay, so now this term is, as x approaches to infinity, what will happen to this term? Will go to 0 provided s has to be positive. That decides our domain. Okay, now coming back up here, so I got here minus y0 because this term is gone. This term I can pull this s out, and that is 0 to infinity e to the power minus sx yx dx. Now what is this? Laplace transform of y of x. So we converted the Laplace transform of y prime into the Laplace transform of y, because this whole thing is nothing but Laplace transform of y. S is already here, y0 is here, and a negative sign is here. Now this is the formula which was there on the in the slide here. And that's what I was deriving by definition. So we get this. Okay, now I will not want to derive the second one. Is there a short way of getting the second formula? I want to get this now. I don't want to do this calculation again.
Just take this one, turn them all to y primes, and then do it again.
So I want here, I want y double prime, right, and I want here then further y double prime. So basically I will replace my function y with y prime. So if I do that, if I replace this function y with y prime, then in this outcome we will have what?
All y primes.
All y prime. So but we want Laplace transform of y. Then I can handle this particular term and place this whole formula there. And if you do that, you will exactly get this expression up here. Okay, because minus y prime 0 will come because of y prime. And then you are plugging s is already there and you're plugging this. So you can see it very quickly. So replace, that's a good observation, replace y prime x, or I should say y, with y prime x. And if you do that, your expression is Laplace transform of y double prime is minus y prime 0 from here s Laplace transform of y prime of x.
And that's just what we just saw.
And that's just what we exactly we have computed up here. So we will just place it here. Minus y0 plus s times Laplace transform of yx. And that's what exactly we have the formula up there. What made this possible? So nicely everything is coming out and it's equals to the formula. Something is going on here.
We made it continuous, right? We took discontinuity, we made it continuous.
Continuity lies within the Laplace transform. Yes, Laplace transform is continuous. But what else is happening? I mean, you said to me that replace y with y prime. Okay, I agreed to you. Y with y prime. And I will do that. And if you see the intermediate steps here, why this is giving us y prime here and Laplace transform of y prime, and then we plugged it back. What is basic feature here which helped us to get this?
Well, we chose our parts in such a way that we would never mess with that y prime. So we never have to do anything with it. It just falls all the way through. Yeah, you know what I mean? We manipulated the situation so we never had to screw with the y prime, really.
Right. So here y double prime, this became y prime
Yeah.
after integration by parts. Y double prime integral is y prime, and this will be y prime, right? And then when you plug the limits, this is gone irrespective of what it is, whether y or y prime, and this one is y prime at 0, and then you have Laplace transform of y prime. But the reason this all happened is because of the linearity, because of this integral nature. If this integral is not there or something else is there, it might not just changing a function and you basically eventually in the final product you are changing the function. The reason this is happening is because Laplace transform is linear. That's the reason. If it's a non-linear function, then there might be some problems here and you might not just replacing y with y prime. Okay, at any rate, now you have these two expressions. You apply this in the differential equation and you are getting algebraic equation. So I will take now some time and do two examples here. One example will be, so these you can get from the table. I would like to do this one. Maybe I can do Laplace cosine or sine, whichever. I want to find Laplace transform of cosine x. I don't want to use table. I want to make use of these formula which I derived just now. And I don't want to make use of definition also, because that will be more complicated to integrate like this. That would be more work in terms of integration by parts. I don't want to do this as well. Is there any... So how will I use the above two formulas? So let me go and copy them. That's what I want to use to compute Laplace transform of cosine x.
So you're going to say the little pause of cosine x is equal to the double prime of it, right? Cosine x.
But then I have to solve that one. So somehow I want to use these two, and somehow I want to use these two formula and I want to compute cosine x. Laplace transform of cosine x. I don't want the solution, I just want cosine x. Basically what I'm saying is, if you think this as a solution of a differential equation, I don't want to, we already have a solution which is cosine x. What we want to find is a Laplace transform of that. So now I am asking you to think backwards. Given the differential equation, you can compute Laplace transform of a solution. Now, given a solution, can you compute a differential equation whose solution is that function and then find a Laplace transform of that function? You see what I'm saying? So give me the differential equation whose solution is cosine x. How will you find a differential equation? You did it, na? Homework first. Given a solution, you were finding a differential equation. How you were finding the differential equation? Right, so do it. dy over dx is? What is y, by the way, first of all? I want differential equation whose solution is cosine x. I think day before yesterday also I gave you differential equation whose solution was cosine x. Yesterday also we did a problem whose solution was cosine x. So differential equation whose solution is cosine x. Okay, then what? Oh, you are saying this is a differential equation whose solution is cosine x? Well, if I make use of this, then the problem is again I have to find the Laplace transform of sine x. I just don't want to find it at all. I just want to make use of these two formula. Go one more step. And what is that? So this will imply y double prime that's what I wrote it down yesterday, day before yesterday on the board. The characteristic polynomial whose roots are plus minus I, it can be lambda square plus 1 only. And lambda square plus 1 is equals to 0 imply lambda plus minus I, so cosine x and sine x will be forming a fundamental set. So differential equation, this will work. Now let's specify y 0 and y prime 0. Y at 0, you know, because you know the function, you know y at 0 is 1. Cosine 0 is 1. Y prime at 0 is just yx is cosine x, so you know what is y prime at 0. What is it? 0. Okay, so you have differential equation, you have initial condition, you will take a Laplace transform both the side of this. So take Laplace transform both the side, you get y double prime x plus yx Laplace transform should be equals to Laplace transform of 0 function. What is the Laplace transform of 0 function? Why? Why?
minus x prime function of 0, which always integrates 0.
An integral of 0 is 0. Okay. So Laplace transform of 0 is 0. Sometimes students write integral of 0 to be x, so that's why I just want to make sure. Integral of 0 is 0. Okay, so what will happen on the left hand side? Y double prime x plus Laplace transform of yx, right? Linearity. Using linearity. Now we will use this formula. So what is the Laplace transform of y double prime from the above expression? Minus so this would be the Laplace transform of y double prime, and for y Laplace transform I will keep it like this, equals to 0. Now let me grab the coefficient of Laplace transform of y, which are s square plus 1. What is y prime 0? It's 0, y 0, 1. So s I can pull it to right side, right? So Laplace transform of yx will be what? S over s square plus 1. Right? So s over s square plus 1. So now y was cosine x. So Laplace transform of cosine x is s over s square plus 1. So we didn't do any integration here. What we did, given a function, we found a differential equation, and since we already knew the function, we know the initial condition also, and therefore we just took advantage of these two expression of Laplace transform y double prime and Laplace transform y prime. There was no y prime term. If it was here, then I would be making use of that as well. But what is very important to note at this point is this: the coefficient of Laplace transform of yx is what? S square plus 1. And what is the connection of this coefficient with the differential equation? What is the connection of this coefficient with the differential equation? Or something which you have learned before. S square plus 1 and any connection with the differential equation right away. What is the characteristic polynomial of this differential equation? That's exactly you will get every single time. The coefficient of Laplace transform of yx term will be nothing but the characteristic polynomial of that particular differential equation. So if you end up getting something different, that's not right. Okay, so this is a CP. Okay, so this is how you will compute the Laplace transform of one of the trick to compute without integrating. Here are the sum with the formulas here. Now let me do one differential equation and solve that differential equation using Laplace transform. We will not be finding the solution because for that we have to invert it, but just the Laplace transform of a solution. Okay, so these are the similar problems of as you have in the web work. If you go up here, and Well, these are asking inverse. I don't want to go to the inverse right now. Inverse will take some time. Let me go to some problem which is not asking inverse but asking you to compute. So for example, this one. So you have a differential equation and you can say, oh, why are we doing this Laplace transform in this problem? Wait, I know we can apply a method of undetermined coefficient. Yes, you can. But the problem is saying using y for the Laplace transform of yt. So you have to use a Laplace transform. Okay? But yes, you can solve this problem without Laplace transform as well. Okay, so let's get started. This is a differential equation. We will first find the Laplace transform. Once we will have Laplace transform, we have to invert it back. But this problem is just asking Laplace transform, so we will leave it at that stage. Okay, so Laplace transform of y double prime minus 6y prime minus 7y is equals to Laplace transform of sine 60. Two functions both are equal, that means their Laplace transform has to be equal. So okay, then just using linearity, y double prime x minus 6 is a scalar, I can take it out. Laplace transform of y prime x minus 7 times Laplace transform of yx. And it's the same as Laplace transform of sine 60. Okay, so now we will apply the formula which we derived above. Laplace transform of y prime was negative y at 0. And if I remember correctly, it was plus s, right? Laplace transform of yx, right? Was it plus or minus? Plus. And this one was coming by applying a prime here. So let's apply a prime here. Sometimes if you forget them, then just remember what is Laplace transform of y prime. And if you forget that also, then just do integration by parts and compute it. So sine 60. Okay, so let's simplify this further. Y prime 0 plus s times minus y 0 plus s Laplace transform of yx minus plus minus s Laplace transform of yx minus 7 Laplace transform of yx equals to Laplace transform of sine 60. I will collect all the terms which are containing Laplace transform of yx. So if I do that, then this is one term, this is another term, and that's the last term. Okay, so I get here s square minus s, and I didn't multiply it 6 here, right? So I missed the 6 here outside this bracket, so that way we will have a 6 here and we will have 6 here, correct? Okay, so this 6 will be coming, so this term and this term, so it would be 6s then, and minus 7. Now you can see that what is this expression equals to? This thing. Characteristic polynomial of this. So we have further some of the terms left here. So let's go up and see what are the initial condition. Y at 0 is negative 4. y prime at 0 is 2. So let's scroll it down. So y0 is negative 4. y0 negative 4 means negative 24 here because of this term. Then this is, we have taken care already. Here we will get 4s, okay, from this one, and y prime is 2, so we will get here minus 2, and this is equals to Laplace transform of sine 60. So let's just push these terms on the right. So we have here 4s minus 26, so it would be minus 4s plus 26 plus Laplace transform of sine 60, and here we have s square minus 6s minus 7 Laplace transform of yx. Okay, now what is the Laplace transform of sine 60? You can make use of a table at this moment. So sine 60 is, this is hyperbolic, here it is. So this is 6 over s square plus 36. And you have here minus 4s and 26, and then you divide the entire expression by this. Now this is, you can see, is an algebraic expression. Solution by x we still don't know, but we know the Laplace transform of that solution of this differential equation. So this is what we have to place it in the web work, and that will be the answer for this problem. And they are denoting this by capital Y of s, because this is a function of s. So this is a Laplace transform of y function, and that's what they are asking. To invert it back, to take inverse Laplace transform both the side, the key to do that is you have to integrate this eventually. So well, integrate in the sense that you have to get expression of s, and then you have to see which one was giving that expression of s. Now to get those simpler expression, it's not easy. As you can see, it's a polynomial down there. So what you have to do is you have to do partial fractions, and by partial fraction you will get the simplified expression of s, which you will check from the table and then write down the back inverse of it. And we will see the next time more in detail how to find the inverse. But this is the idea. So what are the main key features of Laplace transform? They increases the regularity of a function. If it's a discontinuous function, it makes it continuous. Laplace transform is linear. If you apply it to the combination of function, you take it individual function. That works. Laplace transform helps us to solve the differential equation where right hand side is discontinuous. And the last part is, every time whenever you are solving, you will get a coefficient of a Laplace transform as a characteristic polynomial associated to differential equation. Now you would say, well, if a differential equation involves non-constant terms instead of 6 and 7 non-constant terms, then is it true as well? Well, you don't have right now any examples in which we will be computing a Laplace transform with no constant coefficient terms. If that was the case, then we have to do integration by parts on every single term, and we don't have exactly the formula of y prime to plug it here. and we have to handle them by integration by parts. We will consider if it's x times y prime, it has to be e to the power minus sx times that entire thing, and we have to do integration by parts. But since that is not here the case, and even in the entire every section it won't be there, so you would always end up in characteristic polynomial. So basically you are solving constant coefficient second order differential equation with right hand side discontinuous. So here is one of the example which is kind of preliminary here, so we can plug the answer here and check as well, but let me. So here also they are asking you to find, and as you can see, once you have computed, they are asking you to do partial fractions. So once you do partial fractions, you can now very well say that the inverse of this will be capital A times e to the power minus ax, right? The inverse of this expression. And inverse of this was capital B e to the power minus bx, because these are 1 over that, so its inverse has to be exponential function. Exponential function Laplace transform is 1 over s plus a, 1 over s minus a, right? So suppose what I am saying here is, if I ask you what is the function, give me the function back whose Laplace transform is 1 over s minus 3. So L of fx is, so fx has to be e to the power 3x, right? So if I say L of fx is a over s minus a, then my fx has to be, a is just a constant, e to the power ax, right? Backwards. And that's what this decomposition is saying, that once if you have a function and if you decompose them, then their inverse will be a e to the power ax plus b e to the power bx. That would be the function backwards. Okay, so but you would say, well, why individually? It turns out inverse Laplace transform is also linear. Okay, so I was about to show you one last thing here. Okay, so this, not this one. There's one example in which we have this one I will do it next time. This is also interesting. You can think of a differential equation whose solution is this. It has to have a complex roots. Complex roots 2 plus minus 9i. Complex root. And once you do that, increase the multiplicity by 2, because complex root will not have. So you can do that way, this differential equation, because of this t appearing. If t is not there, then it will be much easier for you. Well, still it will involve some calculation. E to the power, if it's just e to the 2t, and what was there? Sine 90, right? So then it is easy to go back, lambda minus 2 plus 9i, lambda minus 2 minus 9i, and multiply these things out, and I will somehow magically will disappear, and you will get a polynomial whose roots are 2 plus minus 9i. And that lambda you replace by y prime, lambda square replaced by y double prime, and you get differential equation, right? So this is for this. Now if you have a t up here, then what will you do?
It's the S over S minus. I mean, S on the top. I mean, T.
You have to make use of something which you have learned.
So there's an repeated rate.
Right, but do you want to take that route? Because that way you would be making it fourth order differential equation. Because complex roots occur in conjugate pair. If you increase that multiplicity, you are making fourth order differential equation. Then you don't know how to find a Laplace transform of y fourth derivative. So, but you know how to handle y prime Laplace transform. So if you know how to compute a Laplace transform of this, and if you take a derivative of this, by product rule, one term will have t, another term will have cosine. Another term will be easy to handle, and first term is what they are asking you. You make use of this and the cosine thing to get the Laplace transform of this thing. Derivative of this function, that's what you have to make use of. Derivative of this function will help you to get the Laplace transform of this function. And don't go with creating a differential equation. Okay, so that was an idea there. Still not working it out completely for you. Here also here may be different trick, little different trick. You can use this t power times function. T to the power n ft Laplace transform. So t to the power n ft Laplace transform is minus 1 to the power n. Laplace transform of ft is fs and derivative of that. So in this situation, when you are doing t square sine 2t, t square sine 2t Laplace transform of this function, if you are trying to do, then you invoke this formula up here. Minus 1 to the power n fns. So what does it mean? Minus 1 to the power n fns. So that means n here is 2, because this is Laplace transform of t to the power n ft. So n is 2, so that means minus 1 to the power 2. Now what is the Laplace transform of sine 2t? It was I think a over s square plus a square, right? So 2 over s square plus 4. I think that's what it. Sine a over that. Okay, so that one is there. So now you differentiate this. This is your capital Fs. Differentiate this twice and place it up here, and that would be your answer. So what I'm trying to say is this notation means derivative of Laplace transform of a function fp. So what is the f prime of s here? And then further you will do f double prime. So, and then you will plug it back, and so this is yet not f double prime, simplifying it. So this will imply f double prime s is quotient rule it would look 24 instead of 2 times 4. 2 times s square plus 4 times 2s, and whole this divided by 4. So the answer for this, let's just simplify this. I'm kind of like, I don't know, running in simplifying, still I have some time. So this one would be minus 4 over s square plus 4 whole square, and this one I will cancel this term one of them, so 16s square over s square plus 4 whole cube. Now this whole thing I will multiply by minus 1 square, which is plus 1. So okay, basically this is the answer. Usually this there's a button in this pen, and if you press it will paste it, the whatever you copy it, but today I don't know why, maybe somewhere pressed or something, so it's not working, so I have to every time go back and paste it. Okay, so this is the expression for your this Laplace transform. So this here notation means nth derivative up here, this one, nth derivative of the Laplace transform of the function. So in exam you should know this, you will be getting this table, so that's not a problem, but you should know how to, given say this problem, how to find Laplace transform solution, or given a function, how to find the Laplace transform of that function. Now if that function is in the table, then you can give like that, but if the problem is asking use definition to find the Laplace transform of function, then you will do integration explicitly, 0 to infinity e to the power minus sx fx. If problem is asking define Laplace transform, then you need to define Laplace transform. What is mean by Laplace transform? So I am throwing bunch of questions here. So right, and you should know how to use linearity of Laplace transform, and I will be posting these slides right now. So that's it for today. Tomorrow we will do review, and day after tomorrow you have exam. Weightage of the material which we covered after the test 1 will be 60%. The material which we covered before test 1, that will be 40%. So just giving you the heads up to the weightage. Okay.
How many questions?
Well, 75 minutes. So same around like 6-7 problems. Yeah.